Okay, I'm audible, right?
Yes, sir.
Thank you. Okay, let's quickly recap what we were doing yesterday. So we started with the OpenGL, or the characteristics of OpenGL. So we have seen that OpenGL is like a low-level software, and also can be thought of as a high-level software because it has access to the hardware directly, and also it's independent to the hardware, and it sits somewhere as an API between the hardware and application program. And then basically we have seen what is a glut and glue, because the core OpenGL library doesn't have much functionality regarding the windowing system or mouse or keyboard. So that's why we use glut. And also for more sophisticated libraries, we need also glue. So it comes as a full package, like a glut plus glue and plus the core OpenGL. And then you can do your graphics applications. Okay. So we have also seen that it can work in a client-server fashion, although you have to do it by yourself. But it has it offers the functionalities for doing these type of things. Um, Also, OpenGL code is event-driven code, so it waits for an infinite loop, and so it's unlike the sequential type of programming where you have defined actions. It does like a waiting net loop, and whenever there is an event occurs, then actually something happens. Okay. And then we have seen it as a state machine, and with DL enable, disable, and basically the states remain the same until you change it, and this happens for all type of comments. Okay, these were the versions we were discussing. So it started with 1.0, and now it's probably 4.6. So we talked about shaders and what is like a shading and these type of things. So this is like a glue and glut library. So basically this one we'll see today in the lab, but if you include this gl/glut.h, that should automatically include everything. Yeah. Okay, so we stopped at the OpenGL pipeline somewhere in the middle. Okay, so regarding the pipeline, let's do it again. So basically you have your commands. So again, this pipeline is also a kind of simplified version of the original pipeline that OpenGL provides. Um, However, like there are many other simplified versions and also many other sophisticated versions. So this version is usually taken it from the OpenGL Redbook. And by the way, I have shared some resources in Teams. You can see in course, I think course notes or course class materials. So inside that actually you will see the lectures. So I will share today the this whiteboard stuff also. Also in the for the labs also I will share everything there. Okay, and I will also share the lecture as well. Okay, so this rendering, so this is like the rendering pipeline, right? Okay, so I didn't write it here. So this is like a rendering pipeline. Okay. So what is a rendering? So the rendering is the process of generating a photorealistic or like a non-photorealistic image from a two-dimensional or three-dimensional model by means of a computer program. Okay? So that's what we call by rendering. Okay, so first of all, you have your commands. So that means you tell what is to be drawn and how it is to be drawn. And these commands can be of of two types of data or two types of commands. So one is like most like a geometry data. So you basically tell about like drawing some curve or surface or things like this, or you directly talk about like pixel operations. So that's why we have two branches. So one is for this geometric data, so that we call vertex data, and another one is a pixel data. And any type of data you have, you can store it somewhere. This is called the display list, and in the display list you can either process it immediately, so which is called the immediate mode of processing, or you can put it in a batch mode. So this happens when there are multiple windows and you have animations. So sometimes you have to keep it and store it for sometimes, and then do it again in the next iteration or after sometimes. So that's why we have this kind of it works as a kind of buffer. So so this is where actually everything can go from here to here, and then eventually after this. So let's consider the top branch, so vertex data. So after this vertex data block, so basically you have to evaluate this like a curve or surface or any kind of mathematical operations you provide. And so basically you approximate the curves or surfaces and everything. And this is basically done by this block. It's called the evaluator block. So evaluator block is the approximation of curve and surface. Okay, so after the evaluator block, what happens? So basically all these vertices and everything, as I mentioned that OpenGL deals with primitives. So that means lines, points and circles and all these type of things. So the vertices are to be mapped into the primitives. And also there has to be done some sort of transformation. Although we'll look at the transformation later in the viewing lecture, but just for the time being, what happens? So let's say this is your world or world coordinate system. So this is, let's say, the world coordinate system. So we call it WCS, and there is some object here, whatever. Okay, so it has a coordinate system. Let's say X, Y, Z. X, Y, Z. And sometimes when you take it from a camera, so camera has itself a coordinate system. So this is called camera coordinate system. Let's call it UVW. Also, your device, wherever you will display your things in the CRT monitor, that also has a coordinate system. So this is called like a device coordinate system. So let's call it, I don't know what to call, PQR or whatever. This is not a good name, but anyway, let's use it. So what happens whenever you are taking a photograph from a real world or you're trying to model something from the real world, so you have to do this type of transformation. So we'll see what is a transformation. So this is called a transformation. So transformation between a coordinate system. So you have to transfer from XYZ coordinate to UVW coordinate system. And also from UVW to, you have to do it like PQR coordinate system. So this is also a transformation. Okay. So this is a simplified version. There are many others also in between, because the device coordinate sometimes has to be normalized. So they have to be within some range or something like this. So, but let's say for the sake of simplicity, so there are some transformations should be done in between. Also, not only transformation, in the first lecture, probably you remember that some parts, let's say this is your computer screen, and there are certain things that are like too big to fit into the screen. So basically, let's say you have a line like this, something like this, something like this, or this. Okay. So it's not that everything can be fitted in your computer screen. So certain things can fit, certain things cannot fit. So this part has to be discarded, right? So this part has to be discarded. So this is completely discarded, this is completely discarded, this is completely discarded, and you keep only these three parts actually. So this process is called clipping. We'll see how to do clipping later. So this is called clipping. So all these type of things actually has to be done within the pipeline. So these clipping things like this. We can also do it manually with some clipping algorithms, but OpenGL handles it very nicely actually. Okay. So there is one block that performs, like after you have this geometric data and approximate the curve and all these type of things, you have to do this type of operations on the vertices to primitives and basically transform into whatever you want in your system. So there is one block here. So there is no particular name for this block according to the OpenGL book. So they call it like a per vertex operation and primitive assembly. Okay, primitive assembly. Oh, sorry, my handwriting is too bad. Okay, so we have an arrow from here to here. Okay, so what this does is, so this is basically like you have vertices to primitives. Okay, and also like a transformation, flipping, all these type of things has to be done in this block. Okay, so so after this, what happens? So that means if you are here, you do this type of things, then basically you like map it to the computer screen, right? So computer screen means it's called like a rasterization. So rasterization means basically you map it to the pixel coordinate system. So then basically eventually after this block actually comes here, this is called the rasterization. So rasterization means basically you do some mapping to the screen coordinate. So basically geometric and pixel data into fragments. So basically we call it fragments. So it's a part of the main memory basically that handles this. So this is called the rasterization. Okay. So after rasterization, what happens? So till now we have done like a basic processing, like whatever objects you have. Do you remember that I was talking at some point about this depth thing? So that means here is your camera and here are some objects. So some part of the object can get occluded and some part can object you can see it from this viewpoint, and some of the parts actually are not visible. Also there are some depth issues that I was talking about yesterday. So basically this object has a depth of d1, so that means distance from the camera, and this has a much larger depth and this one has a much larger depth. So basically you have to have this type of depth effect in your scene so that it looks realistic. But we haven't done yet about this type of things in the pipeline. Although we do it like a rasterization, but after rasterization, we have to do all these type of things, this type of depth issues and all these things. So this is called like a Z buffer. Z buffer is basically removing the hidden part or whatever part we can see and discarding the other parts. So after you map to this like fragments or pixel things, so you have to do this operation as well. So then you can have another block here. So this is called the par fragment operation as the official name of this. So this is called the par fragment operation. So this par fragment operation, what it does basically like Z buffer. So Z buffer means hidden surface removal, or like a color blending, or this type of thing. So there are some color combination or things like this. If it's needed, then it does here. So this is the par fragment operation. And when everything is done, so basically there is nothing else is remaining. So basically we put it like here. This is more like a final stage of the pipeline. So this is the frame buffer. Okay. So frame buffer means is oh sorry, I was wrong actually. So I was talking about in the rasterization I was talking about this is a part of main memory. No, actually it's in the frame buffer. So frame buffer actually is a part of the like a RAM memory. So where actually like a bitmap basically that is stored, that is used for displaying. Okay. So frame buffer is the last stage of our pipeline. Okay. So what happens? So you geometric data, you collect the geometric data, you do the evaluation by approximating the curve and everything, and you map these like vertices into primitives like lines and triangles and circles, and then eventually you do like a rasterization. So you convert it to like fragments, and then you do some operations for removing the hidden parts and also do some color processing in this block, and then eventually you map it to the screen directly, and here you can actually have a display. Okay. So now what happens to the pixel data? So you have your pixel data. So pixel data usually doesn't come in the format that are usually displayed in the screen. So sometimes it needs some appropriate format before processing. So this appropriate format, usually what happens, sometimes you do some processing like scaling, mapping, clamping, and all these type of things. So there are some operations together, and they are basically packed together into a compact form. So this block is basically, we call it pixel operations. Pixel operations. So here is one block. So pixel operation means where it comes from. So it can either come from here directly, or you can do it like a batch mode or immediate mode, whatever you want. It can come from here also. Okay. So this block is here. So after the pixel operation, we are basically mostly done. So pixel operation means we basically we can directly, you can like go from here to here also directly. But sometimes what happens, we have some mapping of the texture. So in the next slide, I will show you what is a texture. So for the time being, let's keep it as a black box. So this is called like a texture assembly. So texture assembly, what happens? You basically have a realistic surface of the object you have created or the model you have created. So here basically it's texture assembly. And from texture assembly, you can go from here to here also. Okay. But usually in the official pipeline, they don't put an arrow here, but actually you can do it here from here also, because from the texture assembly, you can go from there directly. Okay. Okay. So this is pretty much all about the OpenGL pipeline in a like a simpler sense. But if you consider like the main building block, then basically this vertex. So this you can discard like display list. So the vertex data evaluator, per vertex operation, and per fragment operation, things like this. Okay. So now let's see what else OpenGL provides for doing like a realistic display. So I will refer to the slides here, and let me show you. Okay, let's see. So these things I have already covered. Okay, so here the slides are basically mostly pretty much the same that I was doing in the whiteboard. So this is pretty much the same. Okay, so this is basically the pipeline that I was talking about. So here, and some of the links that I have provided, you can read it from the links, and they have a very nice explanations from there. And that's actually the official link. So this is another version like of the pipeline. It's more simplified. So basically, you see that here you have the like the vertex shader or like the vertex operation, and then geometric primitive, rasterization, and all these things, and finally eventually in the frame buffer. So you will see many versions in different textbooks, but pretty much they are derived from the same thing actually. Okay. So we'll quickly see some, before we start with the main program of OpenGL, like the skeleton structure of OpenGL, we see some of the things, interesting things that OpenGL actually provides. Okay. So it provides some drawing operations, first of all. So this is like the basic drawing. So you see here, this is like points, and so GL basically this is a prefix means by it's provided by OpenGL. So all these like primitives are starting with GL and then an underscore. So points, you have lines. So line strip means you can do sequential like straight line drawing. So basically you put the coordinates of the initial and the end coordinate, and it does automatically. So line loop, so you can have a loop from there. Polygon, quadrilaterals, all these type of things. So they are all inbuilt functions or inbuilt variables in OpenGL. Okay. So it also provides some transformations. As I was talking that there are coordinate transformations involved in different type of viewing. So here is a teapot having a coordinate system in somewhere. So basically you see that the handle of the teapot is in this direction, and here actually if you rotate it goes like this. So these type of things can be done using OpenGL functions. And also like a translation. So basically this is x-axis and you are moving towards the x-axis by some amount. Again, it's the same translation around x-axis, like rotation around y-axis and things like this. So these are all very much handy. So this is an example of the Z buffer that I was talking about. Oh, sorry. So this is like a three-dimensional scene, and you see that this object is much closer, and this object is like sitting in somewhere in the far in the scene. So with the Z buffer representation, you see that this is looking kind of like darker, and this is kind of wider. So basically, this is like a 0 to 1 scale mapping actually, and somewhere here is the gray value. So with the Z buffer representation, you can do things like this. Okay. So this is a implementation of the Z buffer. So lighting is another big interesting thing of OpenGL. So there are usually 3-4 different types of lighting. So ambient lighting means it's a surrounding light. Basically, there is no specific light source as you basically see actually. So that's why you see that this is more looking like a uniform lighting, as if the light is coming from everywhere in the room actually, and it's kind of like a darkish. So diffuse light means you define a light source and one part is illuminated, but it doesn't have any shiny effect. So that's why you see that this part is actually a bit black and this part is illuminated. So specular means you have a sort of like reflection like effect, like you have focused light and you see that this particular part is illuminated, but the other parts actually are not illuminated. This is still like kind of darkish, as if you are putting a torch in a dark room and you are pointing to somewhere. So this is a specular light. So sometimes people combine all these things and it's called a Phong lighting. So we'll see what is a Phong lighting model. And you see that this is a very nice example where actually you have the effect of everything. You have a light everywhere and there is a focus point, and also this part is also kind of in the shadow. So these type of things are already provided by OpenGL. Okay. And we will do some hands-in exercise with the lighting as well. Shading is another interesting property. So you see that the difference of the shading in this is a torus, and these three things have a different effect. So here what happens, I was talking about the wireframe, right? So wireframe means just imagine that these are all polygons, like a tiny polygons at the surface of this torus, and you are trying to do rendering or trying to do like a lighting and shading effect separately on each polygon. So if you do it separately for each polygon, then it will look like something like this, and because this is most like a discrete operation. So later people proposed more sophisticated representation, and they tried to smooth the surface by combining the, like, let's say for example, if you're considering one polygon, that means one square on this surface. So sometimes people combine like neighboring polygons also, and then try to have a smoothing effect between them. So that's why you see that this effect, like discrete effect, is kind of gone here, but still it's looking like a blurry. So later people proposed more sophisticated models so that we can have more smooth effect on the surface, and that's how we get this type of effect here. We'll also see all these things in the shading lecture and how this is to be done, and this is actually very interesting. Okay. Okay, now I will talk a little bit about texture mapping. So texture mapping is a big part of OpenGL, and why do we need texture mapping? Um, so there are limitations of geometric modeling. So by geometric modeling, what I mentioned is that you try to define by a mathematical model, and by this mathematical model you try to approximate a shape or surface or whatever. So, but that has some limitations, both in terms of capturing the geometry and also capturing the shape. Okay? Because many natural phenomena, for example, like a cloud, grass, and all these things are very hard to model, especially hair. So there has been a lot of modeling on hair model, a lot of works on hair modeling in computer graphics in recent years. If you're interested in seeing what's going on in the research field in the very recent years, try to look at some of the conference proceedings. It's called SIGGRAPH, SIGGRAPH, and also Eurographics. So these are the two main conferences of computer graphics, and it's a kind of small community. You will see like 100 papers every year, but these are like the top-notch conferences of computer graphics, and you can see some of the very sophisticated works there. So it's a typical thing. Okay, so why do we need a texture mapping, right? So let's consider modeling of an orange. So this is an orange, like the fruit orange. So when I'm talking about modeling an orange, so what do I mean by modeling? I think someone was asking a question that what is the difference between a scanning and a modeling. So I keep the question here in the same context that so let's say if you're trying to scan this lemon or sorry orange and also try to model the orange. So what is the difference? So if you scan the orange, so let's consider scanning using both like a normal camera and also using a laser scanner. So if you take a picture from a camera, then you can capture the exact characteristic of an orange. So that means you see that like a local bumps here, and also you see that very tiny little bumps on the orange surface. So these are all captured in the camera, right? Also, if you take a laser scanner, which has a very nice precision, then also you can capture all these little bumps. But when you are trying to do the like a modeling, using some mathematical models, so sometimes it might not be efficient. So why it happens? Because let's say your let's say this is your orange. Okay, so let's say this is your like orange. Okay, okay, it doesn't look like orange, but anyway, whatever. So, but if you zoom in, for example, let's say this part, you will see that this is actually not very smooth. Like the surface has a little bumps like this in a microscopic scale. So if you try to model these bumps, so what happens? I will try to like redraw in a much bigger case. Okay, so let's say this is your scanning point cloud, right? So that means this is the points on the surface. So that means this is like the points in the surface, as if I am putting the points here. So basically what I'm trying to do is take a laser scanner and shoot a laser here, and that means it records all the points on the surface. So this is what we get from the laser scanner, like the points in the surface. Now this one actually looks like little bumps are available, or you can see the bumps very nicely. But when I try to model them, so that means I'm trying to fit a like a mesh. So I will tell you later what is a mesh, but for the time being, let's assume that mesh means you are basically connecting these points and form a like a triangle on the surface. So that means you are putting a triangle like this and like this, something like this. Okay, so if you do this, then it's good, because you can actually see the surface, or you can use triangle or also quadrilaterals also. But sometimes things get very challenging. You will see that whenever two like a point boundary are very close, so basically triangles are connected like this. So that means this is one triangle, let's say. So what happens? So if this is one triangle, let's say this is one triangle. So what happens? Basically, you lose this part actually. You lose this bumpy effect. And eventually, if it starts from here, then you will see like a smooth surface instead of this type of surface. So that means so this was your scan, and this was your model or polygon model, right? So they are not matching here in this case actually. So these type of problems are actually happening in these cases. Is it clear what I'm trying to say? If you have any question, let me know. So this type of effect is very hard to model actually. So that's why people came up with the other idea of texture mapping. So let's see. Okay, so let's consider the modeling of an orange. So what happens? We start with a orange colored sphere, but that's pretty simple, right? I mean, first of all, the orange shape is not exactly the sphere. It has some bumpy effect in the local coordinate, and also like the color effect. Sometimes you won't get these little bumps also on the surface. So what you can do is replace with a more complex shape. But complex shape means what? Like oval or something. But again, I mean, let's for the sake of simplicity say that we have a complex geometrical shape, but it doesn't capture also the small dimples, like very tiny dot kind of thing on the surface. So that's why it's very hard actually to model this shape, even for a simple orange. Also, it takes too many polygons to model all the dimples, because here, as I was mentioning, so you see that if I do this type of modeling with triangles, so how many triangles will be there if I have these type of, let's say, like 20,000 little bumps like this, then how many triangles will be there? So if there are like 20 triangles here for one bump, and then for 20,000 triangles, just imagine how many bumps will be there. So it will take a huge time to process everything. So that's why it's not very efficient to do everything with these polygon models or triangles. So that's why we have to come up with another idea of doing something. So too many polygons to model all this type of models. Okay. Okay. So the idea is that take a picture of a real orange, scan it, or like process the picture and paste into a simple geometric model. So that means your simple geometric model is a sphere, or like a little bit sophisticated version of a sphere. You take a picture of an orange for the color and also these little dimple or bump effects, and basically paste into the model. So what is mean by pasting? This is actually called the texture mapping. So pasting this into the geometric model. But it's not as easy as we are thinking of pasting this. It's not like a copy pasting as we usually see. So there are many other coordinate systems involved for doing this. So, but still it might not be sufficient because the surface might not be smooth, because we are relying on some like a real photographs, and sometimes we need some smoothness also in the surface. So it's sometimes it's not up to the mark due to the application constraints. Also, we need to change the local shape, because you see that the like top part or the bottom part of the orange, it has a little bit of curviness. So how to get this? You cannot do it with a regular sphere, right? Because there are some like a local geometry that needs to be tweaked. So that's why this bump mapping has to be done. So that means you have to have a sphere, and also then some. So this sphere is like a global shape, right? But this particular thing is a local shape. So that means you have to combine the global shape with the local shape and eventually put it in a full package, right? This is not easy. So that's why it's a hard problem actually. So texture mapping has many types of texture mapping. Mostly there are three types of texture mapping actually. So first type of mapping is called like a normal texture mapping. So it uses images to fill inside the polygon. So that means we have a polygon. So that means this is basically made up of triangles and quadrilaterals or whatever you have. And then eventually we take images and then fill the surface. So that means fill surface means so we have let's say this is one surface, okay? Let's say this is one surface, and you approximate this surface by means of triangles. So these are my triangles, okay? That's how it looks like, okay? So what texture mapping does is that, so basically, so texture mapping does is basically take an image from somewhere and then basically fill this with the same color, and then basically it looks like the material of the same color actually. So that's what it happens. And just imagine this is in 3D, okay? And then it will get exactly the same color as that we have here. So this is one of the process of texture mapping in general, okay? So this is called like a normal texture mapping. So another type of mapping is called the environment mapping. So use the picture of our environment. So here you see that the picture of a building and also probably from the road. This is actually mapped here. Is in the same process that I was talking about, like pasting. So this is another part of texture mapping. Okay. So this bump mapping, this is actually very interesting. So it emulates alternating normal vector during the rendering process. So what does it mean, emulating the alternating normal vector? Uh, Let me explain a bit about this. So what happens? Let's say this is one object, or let's say one sphere, okay? And let's say we have a light source somewhere, okay? So this is a virtual, of course, okay? So now what happens? If what do you know what is a surface normal? Let's say if I have like a surface, so the normal actually points like if you take 2 points p1 p2 and like p3 p4, then you can do it by the dot product and cross product, and that's how we get the surface normal, okay? Do you know about surface normals, anybody?
Yes, sir.
Okay. If you don't know, then let me know. So surface normal is a very simplistic idea. Okay. So what happens here, what we are trying to do to compute the surface normal according to the light source. So that means if the light source is here, so the light is pointing, let's say here, so this surface normal will point exactly here, right? And this surface normal will point like this. It will look like this. So this is completely opposite face. So that's why the surface normal will look something like this. Okay. So if you have this, then basically you will have a smoothing effect. So that means this part is a kind of shiny and slowly it's actually diminishing. So that means the light amount will be diminishing in this direction, and also it will be diminishing in this direction. And eventually here at some point, probably will have like a zero effect because it doesn't see from here, right? So that's why it's looking like a smooth surface. Because we have a very nice transition of the surface normal from here to there. So now what people have been trying to do with this type of texture mapping is that, so they try to alter the surface normals kind of randomly. So that means if you have this, and let's say we are trying to use a similar type of surface normal, so tweak the surface normals a little bit. So that means, let's say this one looks like this one like this, even this one like this one like this, something like this. So this is called a perturbation of surface normal, part of the surface normal. So what happens in this case? So if your light source is here, so let's say here is the light source, and if you have a perturbation of normal, then you will see that this part is like, let's say this part is more illuminated, and also sometimes you see that the next one, the normal is completely in the opposite direction. This part is a kind of blackish. Again, the next part, sometimes it's towards this light source. So this part you will say that is again illuminated. So that's why we'll see that there are lots of little points or little parts where the surface normals are actually pointing to different directions. They will have this type of like little bit of darkish effect. And if you have a very dense surface normal for all the points, then you will have a like a bumpy effect like the orange. So this will be something like this. You see here there are some little tiny dots. So these can be modeled using this type of alternating surface normals. But if we have a smooth surface normal, then it's not possible because it will have exactly the same effect that we have on a regular shape. So that's why this one is called the bump mapping. So usually here, even in the uh, the three-dimensional model of an Earth, they usually try to do with this type of effect. You see that some parts are actually kind of blackish and some parts are shiny. So this can be done with this type of things, and this is done during the rendering process. Okay. So where does mapping take place? Usually at the end of the pipeline. So it's somewhere then, because why? Because very few polygons can pass down the geometric pipeline, because we have seen the pipeline, starting of the pipeline, and it's not that all the polygons actually does the processing for there. So some of the parts, for example, like clipping and all this type of things are done, and some parts are discarded. So very few polygons actually are present at the end of the pipeline, because if we try to do it at the beginning, then it will take a lot of time and it's not very efficient. So that's why we usually do it at the end. Okay. So as I was talking about, so this is basically 3 or 4 coordinate systems are involved, that I was showing, that the world coordinate to the view coordinate to the device coordinate. So it's basically mapping from a 2D image to the 3D surface. Task. So there are some specific techniques for this. So this is basically, although we'll see it in the clipping lectures or viewing lectures. So this is the same thing that I was talking about. You have a coordinate from the texture, and also the parametric coordinate means the curve you are trying to, or the surface you are trying to model. And also this is a world coordinate, and then the screen coordinate. So different coordinate systems are involved. So that's why this is a kind of not so simple task. Okay. So these are pretty much the functionalities of OpenGL in general. So now we can start actually seeing some syntax and some examples of OpenGL coding. Okay, this one I have discussed. Okay, I think let me start with a very basic OpenGL code skeleton. So I think that will be the best thing to do. Let's start. Okay. Just a minute.
Excuse me, sir.
Yes.
Sir, for the bump mapping, sir,
Mm-hmm.
do we like when we do it, do we like individually go to each vector and like change the
You don't have
well?
to. What you can do is, well, of course, I mean, you have to like run a loop or something for all the vectors, but you can do it in a randomized fashion. So you just let's say your normal vector, or like you generate a random number between some value to some value, and you generate for every surface normal, you part up using that random value. That should be fine. But if you don't do it individually for each vector, then it's hard, because well, that takes a lot of time, of course. But
Yes.
usually, in a naive sense, yes, you have to do it by normal vectors.
Okay, sir.
Okay, so now let's see the one basic structure of OpenGL code. Okay, and then we'll explain line by line and then see how it goes. And then eventually we'll finish with some syntax examples and other things OpenGL provide. How much time do we have? 15 minutes. Okay, let's see. Okay, so let's call it a skeleton of OpenGL code. Okay, so as I mentioned, I start from the very beginning. So basically you start including the header file. I mentioned that GL is the main OpenGL library, and basically glut.h. You have to include it somewhere, okay? And you start your main program. So in main, okay. So basically you have some command line arguments, okay? That's very simple, and we do it from here. Okay. So now the first thing in OpenGL, what we do is to initialize the glut library. So this is usually done by this function. This is called glut init, and it takes basically the arguments, and this is GP. Okay. So what is this? Sorry, we are on. Okay, so this basically initializes the glut. Okay, so it basically, when you initialize the glut, it negotiates with the windowing system. So that means after the glut gets initialized, it checks the windowing system in your system. So it may cause a termination of the program if glut cannot be properly initialized, right? For example, there is a failure to connect the window system support for OpenGL. For example, your windowing system doesn't have any support for OpenGL. So then basically glut cannot get initialized, and then basically it gives some error message and basically terminates from the program. But whatever you do, you have to start with this glut init. So that's the initialization of the glut library in your code. Okay. Then basically we have to set the display mode, like how the display will look like in our code. So this is done by glut init display mode. So glut init display mode. Okay. It takes some arguments. Okay. So it sets the like display mode. So that means like as I mentioned that it will like you have to specify how this display will look like and what type of features the display will have. So there are you can check out these functions in the like official OpenGL documentation. You just Google it and then you will find many resources. So glut init display mode takes different arguments depending on the applications or depending on what you want. But let's consider some of the basic ones that usually people use in most of the applications. Okay. So here is called glut single, glut underscore single. So what does it mean? So this glut single is basically means it's a single buffered window. Okay. So single buffered window, or there can be also like a single versus double also. So for example, let's say, so I like it here. So glut underscore single versus glut double. So this is a single buffered window. Single buffered window. And this is a double buffered window. So what does it mean? So single buffered, let's go here. So single buffered window means code is drawing directly to the display. So that means you don't have anything else. So you just have one window and you have one operation, and basically you do it instantly, and then glut single window, that's done. Okay. So double buffer window happens mostly when you have some sort of animation, or you have switching between windows and all these type of things. So let's say you have two buffers in your application program, or you have two window systems, or like, oh sorry, you have two windows. Two windows will be used for like outside at not Windows. Let's say you have two buffers actually. So that means one of the buffer will be used for display and the other buffer will be in the processing mode. So what happens? Let's say buffer 1 and buffer 2. So let's say buffer 1 and let's say this is buffer 2. Okay. So one of them, let's say this is visible. Let's say this is visible. So that means we have put it in the screen actually. The other one is not visible. So this is step 1. Okay. So in the next step, so what happens? So we rendered the buffer that is not visible. So that means we are preparing for these to be getting displayed. Okay. And basically make the just rendered one visible. So basically we call it like a not visible and then make it visible. That means so B1 and B2 get interchanged here. So that means B1 comes here and B2 comes here in terms of display actually. So that means you see this buffer actually is going in the again in the processing mode. So in each frame, so basically what happens, two buffers are reversed. So that means this process, if this process continues, then you will see that this gets interchanged like very rapidly. And there is some like a pause in between, otherwise you won't see a nice effect. So that's why what happens when you use a single buffer window like a GLUT single, you will sometimes use GL flush. So this function you will see many times in the graphics program. It's basically, it's most like a flushing when you do in the C programming. It's also in the OpenGL, it's a GL flush. So it flushes the buffer actually, it clears everything. And in double window, so like a double buffer system, you won't use a GL flush. So you will use a GLUT swap buffers. Is GLUT swap buffers. So GLUT swap buffer means basically this part actually. Okay, so you basically interchange between these two buffers. So this is basically it's done by like a GLUT single and GLUT double. So it depends on the application that you have here. Okay? So GLUT single, and also there is another thing we usually have. So it's the color model. So let's use here GLUT RGB. So that means we are using a RGB color model. Okay. So that means here in this case, so basically this one basically, so this function basically specifies, so it's specify the window property. Okay. Okay. So this specifies the window property. So this is like a typical part of a OpenGL code. Okay. So now we have to set the window size and the window position. So we have initialized GLUT. We have set the display mode, or what type of display we want to see. And then basically we have to tell about the window, like how it will look like what is the shape and where is actually is residing, or what is the size. Okay. So this function is called GLUT init window size. Okay. So GLUT init window size. Okay. And basically you say it here, let's say 500 by 500. That means this is the width and the height. Okay. So basically the window, so basically this is called the set window size. Set window size. Okay. Also we have to show the window position. Okay. So this is called the GLUT init window position. Let's say we start at 0, 0. Okay. So basically this is the X and Y coordinate of the window. So its initial value, initially like if you don't put anything, it's basically -1 and -1. So it gives some error, so it doesn't work. So why they have given -1, -1? Because they are basically, the design was with the motivation that it is left to the windowing system to decide where actually it starts the window, or where actually the window position starts. So we have put it here in the like a 0, 0. You can put wherever position in your screen if you want. So this basically like the set window position, right? Okay. And then eventually when you do this type of thing, so you have to create the window, because this is basically like initializing the window, right? We have used the init position, so size and position. So now we are creating the window actually. Okay, so basically glut create window, and here write something like a simple. Okay, so glut create window will be requested to be created with the current initial window position and size. So that means depending on this and this window will be created. So that means this one actually opens the window. And name it. So if you open the window, you will see that the symbol is written at the top of the window. That's it, nothing else. So with these only three function calls, you can create a simple window. Okay, now here comes is the important thing. Remember that I was talking about this part. Yes, this part. You see that the OpenGL program is event-driven. It waits for an infinite loop. So this part has to be done in the main code itself. Okay, so we have to create an infinite loop, because this is a very simple program, and but actually if you have a sophisticated program, then you have to define everything, right? So this has to be done by what is called the callback system. Okay, let me put the name and then I will explain what is this. Okay. So this is, let's say, for the display, so glut display function. So let's call it my display. Okay, so this is called a display callback. So what is a display callback? So you will, okay, so this is display callback. Okay, so you will see this callback term many times, sometimes in the when you read OpenGL materials or whatever. So callback is a function in which the library glut calls when actually it needs to be known, like when it needs to know how to process something, like when something happens actually. So for example, let's say you use like a key press, or you use some mouse pressing or something like this. So then basically this callback routine is basically finds out what are to be done with this event actually. So that means when I have a, like, let's say if I try to have a functionality in my program where actually the user is pressing Q and the program is actually quitting. So in that case, basically this display callback actually needs to know what has to be done when you press the Q. So that means you have to explicitly specify what is to be done inside that callback function. So here the callback function's name is my display. Okay, so the format of this function is kind of something like this. So okay, we don't have much time, but I will just finish with this. So this the official like a syntax. So so this glut display func, let's say my display. So actually the like the official format is that it returns a void, and this is glut display function. And then basically here inside the format is something like this, void basically start func, and then basically this is void. So this one, this part actually, does anybody know what is this in C program? What is called when we program pass something like this? Like, what is the name of this particular thing?
What function pointer?
Function pointer or pointer to function?
Pointer function.
It's a pointer to function, right?
Yeah,
Because
pointer to function.
yes, so this is a pointer to function. So that means we have to define somewhere. So my display. So inside my display, actually, you have to define everything what has to be done. So then basically, this glut display func actually uses these instructions to see actually what has to be done, and then basically performs this application. So that's why this is called this like a callback function. Okay. So this happens when this is called basically when something happens. So that means something happens means so window resizing or window redrawing. So it might happen that in your code actually you are resizing the window or redrawing something, or also user input is there. Also you have some animation and things like this. Okay. So okay, we haven't finished yet, but let's stop here because the class it's already 12. So maybe we can start from here in the next class, and then I will explain what are the other things in basic OpenGL code, and then probably try to finish. We will try to finish OpenGL maybe in 1 or 1.5 class. We'll see, and then see what happens actually. Okay. And for the labs, today we have one lab and one tutorial. So tutorial will start just after now. So just keep it like a 2 minutes break. I will like close this meeting session and then create a new one. And then people who are registered for 60012, they can join this class if they are not able to join the lab. And other people, then you can do it in the lab session. So today in the lab, since we haven't done much of OpenGL, so we'll just do some installation and basic code running example. That's it. Okay. And then we'll see what happens. Okay. Okay, so we stop it here, and I will see you, some of you after 2-3 minutes, and some of you at 2, right? Okay, so thank you very much.
Sir,
Yes, any question?
sir, if I attend the lab, will I also have to attend the class after 15 minutes, or will it be done in the lab as well?
Which class you are talking about?
So today, do I have to attend both the 1 hour class right now, or
No. This, so basically, this 1 hour class. So this is a tutorial, right? But I will try to combine the labs in the tutorial. So that's why if you can either okay, if you are welcome to attend both, but I will try to compact the labs in the tutorial session actually. But usually 1 hour is not sufficient, so I suggest you to attend the labs. But today we won't do much in the labs, just the installation and everything. So whatever you feel comfortable, I'm fine with that. So there is no pressure on attending everything. Okay.
So means, sir, if we attend either of the one, it will be fine, right?
It should be fine, but try to attend the bigger session because it will be helpful. Because as I mentioned that in the labs, actually, we are not having weekly assignments. So in the labs, I will try to show you, like give you some hands-in exercises, and you practice and then see how things are actually going. So you can attend.
I was intending to attend the lab only. That's why I was confirming it with you.
Oh yes, you can attend the lab only. So you don't have to attend the session right now after this class. So that's absolutely fine. Okay.
Okay. Thank you, sir.
Okay, no problem. Okay, so we'll start after 2-3 minutes. No worries.